Hello, CS161. Welcome to week two of this fun semester in computer security. This is one of the TAs, John, and very excited to take you through this walkthrough of the second discussion. So before diving in, hope you are fitting into the class, feeling okay, and settling in during this past week and a half or 2.5 weeks. As usual, if you have any questions or need any particular help, whether it's conceptual, technical, or tailored to you, we as the TAs are more than ready to help you guys, whether it's through Piazza or through office hours. Don't hesitate to post and we'll get to you as soon as possible. Great. So diving into this week. So last week we talked a little bit about x86. We talked about security principles, and we talked about GDB. A lot of the basic tools and the basic concepts in this class that you'll probably find yourself using repetitively throughout the course. So with this week, what we are diving into now is more practical and more on the side of software security. So with this class being taught in C, which is a pretty low-level language, we are pointing out some of the popular vulnerabilities that you could find in C code that is sort of a product of the language being a relatively older one, and therefore having sort of a lot of exploits that were only realized a little bit later after the language was originally developed. So you'll get to we'll debug some code, take a look at what the errors are and what kind of exploits they could lead to. And then we'll move on to question 2, which is a potpourri of sort of different C memory defense mechanisms. So we will revisit a lot of the concepts in class, clarify them, and then sort of get you in this context of thinking about, given this defense or given this attack, why or why not would some particular outcome occur. And then last but not least, in question 3, we'll visit this concept of a trusted computing base. So also known as a TCB, this concept comes up a lot in security, which is why we're putting this at the beginning of the class. Great. So without further ado, let's dive into problem number 1 about software vulnerabilities. Great. For the following code, assume an attacker can control the value of the variable basket passed into a function called search basket. The value of n, another variable, is constrained to correctly reflect the number of cats in basket. So the keynote here is, when you run into these kinds of questions, the keynote here is that an attacker is the one who is looking at this function and trying to exploit it. So we're aware here that there are 2 values that can be passed into this function. So the idea is that this attacker is going to potentially attempt to pass in some malicious input. And the question here is asking, given the what kind of malicious input could lead to what kind of exploits in the code. Great. So the code includes several security vulnerabilities. Circle 3 such vulnerabilities in the code and briefly explain each of the 3 on the next page. Cool. So before diving into the code itself, some of the things to keep in mind are when you look at these problems, some of the vulnerabilities we discussed in class are buffer overflows, stack smashing. You may have like formatting errors with strings, so like with printf, certain formatting syntax may lead to unwanted behavior. You could potentially have errors due to incorrect evaluation of different numerical types, so unsigned versus signed is something that comes up. And when you're actually evaluating the code, it's probably good to look for, first of all, the inputs, that the attacker provides. So in this case, it would be n and basket, and paying attention to how these variables are used throughout the code. Something else we'd recommend looking at instinctively when doing these kinds of problems is looking at buffers. So you have like one on line 2, one on lines like 9 and 10. And the idea is that, buffer overflows, per the name, usually exploit buffers that are not properly guarded. So that's something to pay attention to. And last but not least, and we'll discuss this further, of course, something that should catch your eye right off the bat is in line 28, there seems to be a system call. So system calls are possible in C, where the idea is like, you write some code, you can format a command line argument, and then you can run it from the compiled C executable. So the problem with this is if there's input, like in line 26, where the attacker could provide or some malicious value as a parameter, and then that parameter gets formatted and incorporated as a command line argument, and then run, line 28, when that system call is made, is running under the permissions of a user, not the attacker. So the issue there is like, with different privileges, this could lead to, unwanted system calls being executed. Great. So that's just sort of like a laundry list of things to keep in mind. But now let's dive into code and understand this first before pointing out some of the issues. Great. So in the first 4 lines, we have this cat struct. So remember, in C, there's not really a concept of classes. You can define these sort of like type aliases, which are really just structs, and these structs can have fields. So in this case, the cat struct, or the cat sort of type, is going to have a name, which is a character buffer with 1024 spaces, so kind of like a string. And with line 3, we have a cat's age, which is a type int. Great. So from line 6 to 7, we can kind of discern that the goal of this method is that it takes in this basket array, which is supposed to be sort of an array of cat items, if you will. And the basket contains at most 32 cats, and that is indicated by this size underscore t parameter here. So size underscore t, in case you're not sure what that is, that's really just like an alias for a numerical type. So in this case, this is really just like an unsigned int that specifies the length of basket. And the goal of the method is to return the number of kittens, or -1 if there's no kittens. So the idea here is like we go through all the cats in basket. If a cat is young enough, considered like a young cat or a kitten, then we're going to record that information and then indicate how many kittens are in this basket of cats. Great. So on line 9 and line 10, we have a couple of buffers being made. So with line 9, what we have here is, again, a struct, an array of cats. So similar to the basket, it is initialized to size 32 to account for, like, if all of the cats in the basket are kittens, then the kitten struct has enough space to read all of them. With line 10, we have a character list of the kitten names, a character array of kitten names. So we have the kitten names, which is 1024 slots for characters, and then this command character buffer with another 1024 slots. And as we'll see a little bit later on, the command buffer is going to allow us to actually write a command line argument, or construct a command line command and then execute it with the system call. So that's a little bit later on. With 11, we just have some pretty straightforward declarations of a couple of int values. So we have I is going to be an index, total kittens is the value that we're going to return, and then names underscore size is going to sort of be a pointer, a memory pointer that we'll see later on with regards to how it's used. Cool. So with line 13, we're doing a very simple check where we're just making the above, the aforementioned enforcement. So as stated in the beginning of this question, the value of n is constrained to correctly reflect the number of cats in the basket, which is going to be a number that is 32 or less. So if we have n greater than 32, then this function is just going to terminate early. Cool. So for line 15, we have this for loop, and then in line 16, we have the condition to verify like whether the cat is a kitten. So is cat a kitten? And it's just based on whether the cat's age is less than 12. In line 17, what we're doing is we're taking the string length of this cat's name. So as you recall, like basket and then index I is going to grab a cat item, and then name is one of the fields declared in line 2 of the cat type. So strlen string length is going to grab the length of that character buffer and then give it and assign it to the value of length or len in line 17. Then what we're going to do is we have this interesting snprintf function on line 18. So there's a couple parameters, and let's take a look at each of them. Here with kitten names, we have this character buffer that we mentioned above and that we declared in line 10. So what we're doing is we're taking sort of like remember from 61C with the character buffer, if you don't dereference it, then the value itself points to like the beginning memory address at the sort of beginning of the character buffer. So what we're doing is we're taking that memory address and then adding it to names underscore size. So this is going to initially be 0, but the idea is that as we aggregate more cats to the basket, names underscore size will increment, so we will be able to find, where the last where the last name was written and where it was left off. So that's this is a memory address. And then we have a length here. So length is just going to be a specification of the number of characters one would want to write to this memory address or to this buffer, right? So as kind of mentioned here below, it won't write more than length minus 1 characters. Great. So we kind of found the length of the cat name, and now we're saying, okay, don't write any more than the cat name itself. FMT here just specifies like the formatting. So here we're using %s, which indicates like %string. So kind of pass this in as treating the value as a string. But we could also have, there's different formats like %d, %c, a bunch of other ones. Great. And then last but not least, this is sort of the value that we're writing in. So we have the name of the cat, and we want to write it to the list of kitten names, which is very cute. On line 19, after we've written the name to the sort of like ledger of kitten names that we have here, we're also going to record the actual cat item in kittens, right? So in 18, we're reading the name. In 19, we're recording the actual cat itself. And then in line 20, we are incrementing this names underscore size delimiter, if you will, by the length. So then the next time line 18 executes, it won't be kitten names plus 0, it'll be kitten names plus the length of the previous kitten, so wherever it left off. Great. And then last but not least, on line 21, we're doing an increment of the total kittens that we've seen thus far. Cool. So hopefully that for loop makes sense. Last but not least, on line 25, we have this interesting condition which says, okay, if we have more than 5 kittens, what we're going to do is construct a command line argument that allows one to adopt kittens. Very, very nice. So on line 26, we have a constant character pointer. So this is, again, is kind of like a string, and we're declaring this as like a constant value. So this constant just has sort of like a fixed command line set of arguments and executables. The executable is like adopt kittens, and then the flags are like the number of kittens and then the names of the kittens, right? So this snprintf, again, it doesn't actually print anything to the command line. Rather, it writes to the buffer. So similar to the use case in line 18, we're writing now to the command buffer that we declared way back when. And again, we're specifying that the command should be no longer than the length of CMD, which is 1024 characters. We pass in FMT, which is the format of the argument, so that was declared in the previous line. And then this dot 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 here, the ellipses I should have mentioned before, that just indicates like if you specified some string formatting. So for example, on line 18, we just had like a single string format instance, and we just pass in a single argument that would be fed as, %s. Here, since we have two, so we have %d and %s, we're going to pass in two additional arguments that will fill in the blank of these string formats. Great. And then system, as mentioned here, runs the shell command given by its first argument. So that's what line 28 is doing. It's going to execute this command as with the privileges of the executable. And then finally, it's going to return the number of kittens in this basket. Great. So that was a little bit long, but hopefully you had some time to read the code. And then now I'd recommend pausing the video, take a minute, and see if you can identify the 3 vulnerabilities. And I'm going to go ahead and explain them. So one of the first vulnerabilities, hopefully that you noticed, is what we call a fence post error. So if you look at line 15, just look at the line in total, take a second, see if you can figure it out. And the issue here is probably an error that you have seen maybe in like a lower division class when you're doing a project. But the problem here is I is less than or equal to n. So that is not okay, right? Because that means that the values would be going from 0 to 32 at most, as opposed to 0 to 31. From 61b, you know that in Java this would result in like an array out of bounds error. So similar to here, we don't have as specific errors in C as we do in Java, so it's very likely that the program could just crash. So that'll probably be the normal behavior where it'll just say, oh, it doesn't see anything here, or the string has been terminated already. But the more concerning problem is that this could be the place where a buffer overflow exploit occurs. So you can imagine, like at line 13, there's a test that ensures n doesn't exceed 32, right? So as you might remember from here, it should be, in theory, we could correct this problem by not only editing what's on line 15, but also making this like greater than or equal to. Because again, the idea is that I is an index. 0 through 31, from a logical standpoint, are the valid indexes. So 32 is not logical. So sort of the lack of covering or eliminating 32 as a possible index could lead to writing in an extra kitten. So what happens is in line 19, if the attacker makes it so that all of the sort of first 0 through 31 items are all kittens, and they all have age less than 12, then the attacker could include a 32th kitten or 32nd kitten, which would write past the end of the kitten's buffer, right? So originally, kittens right here says, okay, I'm going to allocate enough memory for 32 cat items. If we pass in 0 through 31, that's going to be 32 cat items in total. But if we fail to take into account this extra 32 index, the attacker could be writing in a 33rd kitten, which would write past the buffer, and that results in a buffer overflow vulnerability. So that's one of the issues. Great. Awesome. So the second issue is related to snprintf on line 18. So it's not so much a problem with the function itself, but more about the parameters that are being passed in. So if that's a hint, hopefully take a second, see if you can figure that out. If not, that's totally okay. So let's take a look, right? So we have the buffer on line as the first argument, plus the memory address. This seems to be okay so far. Now, the thing to pay attention to is recall that the size of kitten names, like kitten names, was defined to be a character array of just 1024 slots. However, we've also defined the name to be a character array of 1024 slots. So hopefully from that you can start to surmise if we have a cat with a really long name. So perhaps the original intent of the program was, without thinking about this, you would think that a cat name is like, only a couple characters long. But an attacker who sees this could make a cat name that's like 1024 A, so it's just A, a ton of A's. And then what happens is when that first name is written, it fills the kitten names buffer entirely. So what happens the second time, or when the next kitten name is read to this buffer? Well, the first kitten name filled all 1024 slots. So then what happens is the second kitten name is going to overwrite the existing kitten name's buffer space, right? So again, that's a buffer overflow vulnerability. So just to sort of reiterate in a more official way, the idea is that by supplying like really large names for kittens in basket, the attacker can like very quickly write past the end of kitten names. And again, it's a buffer overflow. So the way that you could correct this is either do sort of like a mental calculation of, oh, if I have, like 32 kittens max, and I have sort of, I want my kitten names to be a character buffer of at most 1024 characters, then that means that, each kitten can have at most, 1024, divided by 32, and then you probably want to floor that number if there's a remainder characters at most. So one way to fix this is potentially you could just change whatever the buffer size for name is on line 2 to be 1024 divided by 32 instead, or you can make kitten names declared right here 1024 if you really want that to be the length of a single kitten's name, then would have to accommodate for 32 kittens names, but that's a lot of bytes. Cool. Okay, hopefully that made sense. And then the last solution is, as sort of foreshadowed a little bit earlier, related to the system call. So as alluded to in a sort of more general sense earlier on, when you're running line 28, you're running a shell command, right? So the shell command is going to run, with the privileges of the executable or whoever is running this executable. So the problem with this is when you're running the system command or the shell command that's defined on line 26, you are taking in user input, which is, or in this case, it's input that is derived from the parameters that the user passed in, which could very well be, user input. As we indicated from before, the values of kitten names and total kittens, while it's not directly manipulated by the user, can be very easily indirectly manipulated by the user who provides, a certain special set of inputs. So one of the problems here that is more evident is the problem with sort of the string itself. So anytime you're passing in a string to a command line argument, that opens the possibility of injecting your own shell commands as an attacker, right? So you can imagine the problem with this could be, the input includes some shell command, so nothing stops the attacker from not giving a proper cat name and instead coming up with something really weird, right? So the practical example that we have is if you, in shell commands, the semicolon is a special character that separates commands. So you could very well just call a cat, there could be some input before it that doesn't matter. It's terminated, and then you can input your own shell command here, which is sort of the act of injection, and that's pretty problematic. A pipe which is kind of that like weird vertical bar character, that's also a problem. So just a couple quick examples. But the general idea is user input that's being passed into a system call should be sanitized or avoided in the first place if it's not necessary. Great. So that's kind of the three vulnerabilities. And then there's this last question here, which is describe how an attacker could exploit these vulnerabilities to obtain a shell, right? Or to obtain, yeah, obtain a shell. Great. So as we mentioned before, we have these like three errors here. We have one on line 15, one on line 18 with sort of the sprintf and specifically the length right here, potentially messing things up. And then we have the command injection here, right? So you can kind of string the two together. So the idea is that with your buffer overflow, what you could do is overwrite start overwriting what the material in the stack, right? So as we remember from last week, we have our kind of our stack right here, and potentially we have the values corresponding to we have our the sort of beginning of the stack here, and then kind of like the ending of the stack. And the way it's organized is that there's certain registers that correspond to the variable values here, but maybe we have some special registers like the return instruction pointer or like the stack frame pointer or something like that sitting on the bottom. So what happens is when we do a buffer overflow, the values that we're passing in here could trickle down and then overwrite some important register values there. So by being very careful and calculating sort of like the position of characters correctly, an attacker could overwrite the return instruction pointer, execute arbitrary code. So that's one problem. The command injection one, which is on line 28, that error is a bit more sort of conspicuous in the sense that all you would have to do is pass in like a weird cat name that's really just sort of like a disguise for shellcode. So something that would not be good is like terminating with a semicolon, and then if you introduce bin /sh. So this is the command that corresponds to opening up a shell. So it terminates, bin sh is executed, and now an attacker with the incorrect permissions has access to the shell. Great. So that is part one. All right, so moving on to section 2 of the worksheet. Now we're going to talk about some topics in C memory defenses along with the vulnerabilities. So the purpose of this section is to try to get you to critical think a bit about the attacks, how they work, some of the defenses that we introduced, and then really going in depth on why certain defenses work, what their actual purposes are, and then if certain situations or contexts are changed, is the defense still effective? So mark the following statements as true or false and justify your solution. Feel free to discuss virtually if that is possible. So yeah, feel free to pause and take a minute, but I will dive right into it. Great. So for number one, stack canaries completely prevent a buffer overflow from overwriting the return instruction pointer. So let's identify. So this is going to be stack canaries are the defense against buffer overflow, which is the exploit. Now, when we talk about a sort of exploit, we usually refer to possible sort of, or I guess buffer overflow is more of a sort of vulnerability. And stack canaries are the defense, and usually with a vulnerability there will be an associated exploit with it. So in this case it would be like overwriting the return instruction pointer. So just keep in mind that if you have a vulnerability, there's usually a lot of exploits attached to it. So we'll see that come true like later on. So the main issue with this particular statement is the fact that it claims completely prevents. So you might recall from lecture, stack canaries are pretty useful, but again, they're more meant for detection as opposed to the correct, or as opposed to actually preventing a buffer overflow in the first place. So stack canary is usually a sort of a value that is being put in between a local variable or local variables and the control data on the stack. So the idea is like before a function finishes executing and is returned, this canary is checked. And if it's found that the canary was different from the original value, the code is going to preemptively fail and stop the or terminate the finishing execution of this function. Right? So the problem here is that stack canaries help, but they definitely don't completely defend, right? So the answer to this is false. And practically speaking, some of the ways to circumvent stack canaries is one, simply if there's information leakage. So if there is some way that the canary is revealed, which is possible whether it's through another exploit, for example with format string vulnerabilities, you could feasibly print out or write out areas of memory that you're technically not supposed to see. So that's possible. So to put that into words, stack canaries are only for detection, which is why they don't completely prevent. And then the way they can be circumvented, one is like information leakage, which is definitely feasible through poorly written code or poorly used functions. And the second possibility is just not enough entropy. So remember, the canary is a random value. And this random value, if it's not random enough, could be sort of successfully guessed if the entropy is pretty low. So if you're interested, there's some research from 2011 which found that the Windows implementation of canary, of generating a canary, relied on just a single bit of entropy. So basically, you could just guess true, and 50% of the time, you could circumvent the canary, which is really, really, really not good. Cool. So for number 2, a format string vulnerability can allow an attacker to overwrite values below the stack pointer. So let's kind of formalize this a little bit. So the attack that or the vulnerability is format string. And the exploit that we want to use is overwriting values below the stack pointer. And we don't really refer to a defense in this particular question. So this one, it's really tempting to think that this one is false, and with good reason. So with format string, practically speaking, what we're referring to is the printf function, right? And you may remember, like, printf, the idea is that you can put in a string here, it has some values, and then you can specify these format specifiers like %d, I don't know, %s, %c, and pass in like corresponding values to replace those specifiers. And what it'll do is it'll print out the values in a way that's specified by the format. So you might be scratching your head or asking yourself, like, isn't printf supposed to output values? Like, and this question is talking about writing. Like, this just shouldn't be possible with printf at all. So that instinct is definitely correct, except for the fact that with printf, there actually is a format in which you could write to as opposed to simply print out a value. So I'll write it on the side here, the exploit here, and I'll just title it printf exploit. So the problem here is we're dealing with is this %n. So this format specifier doesn't actually take a function argument and output it, but rather it'll write to the function argument that's specified there. So let's sort of demonstrate this really quickly. Let's just say you have a function called printf, and printf has values 1, 2, and 3. So the idea here is like, you can pass in printf 1, 2, 3, percent n, and then pass in an address here. So the problem here is percent n, the rule that it works by is it's going to write write the number of characters that came before it into the given memory address. So what that means here is, you have, 1, 2, 3. So these are 3 characters, right? So, and let's just say like before this printf, sorry, things are a little crammed. Let's just assume like this int x was defined before the printf. So what that means is 3 is going to get written into the x variable, right? So what that means is like later on in the console, if you output x, what you're going to see is x actually gives you back a value of 3. So this by itself is not the problem, but what this function allows us to do is leverage using, so again, this is true. And what we can do is use printf plus the format specifier n plus the targeted address as our argument to printf. And this allows us to overwrite values below the stack pointer. All we have to do is figure out the address of the value that we would like to overwrite, and bada bing, bada boom, we can overwrite it. So this guy is pretty problematic. Cool. Okay, number 3. An attacker exploits a buffer overflow to redirect program execution to their input. So buffer overflow is the vulnerability, and the redirection of program execution to their input, that's the exploit that we're trying to implement. Now the claim here is this attack no longer works if the data execution prevention / executable space protection / NX bit is set. So that's the defense, right? So in this particular case, the answer is actually true, which is nice to know that there are some defenses that are pretty usable. But to go a little bit more in depth, so the idea here is that, if you want to redirect a program execution to the input, then the idea is that you would be writing and executing a particular program at the same time. So this attacker would need to not only inject code, but also execute the injected code, right? Now, the interesting thing, just in case you're not familiar, is every file has sort of like 3 levels of operations or permissions that can be associated with it. So if you want to try this out, just go on your computer, do an ls-l in your command prompt, and what this -l option does is, in addition to listing files, it'll show you the permissions associated with those files. So I'm just going to abbreviate permissions associated with each file. And part of the sort of permission specification is that there are 3 operations, which are read, write, and execute. So these are sort of like 3 different things that you could do with a file: read, write to it, or execute it, right? So the reason this is true is because the whole point of the NX bit, which is, the aliases are data execution, prevention, and executable space protection. The whole point of it is to prevent the same area in the program to not be writable and executable at the same time. So the hopefully you might be able to figure out from the name, data execution prevention, executable space protection. The idea is that, if you can write to it, great, but you can't execute at the same time. So if the NX bit is on, then, no writing and executing at the same time. Cool. Great. Okay. Number 4. All right, so if you have a non-executable stack and heap, so that's kind of our defense here, buffer overflows are no longer exploitable. So here is our vulnerability, and we're claiming that, ding dong, the witch is dead, buffer overflows no longer exist. Hopefully you can garner from this discussion that with a lot of these kind of absolute claims of this vulnerability is just done for with sort of a single defense tend to be false. Now that's not the right way to answer the question, but just sort of something to keep in mind, right? So this answer, as we kind of revealed, is false. And you might be scratching your head a little bit, which totally makes sense if you said something like, well, didn't we see from above that the buffer overflow vulnerability is mainly centered around exploits that allow one to write or like inject code and then execute that code? So isn't the whole idea that, if your stack and heap located in processor are not executable anymore, then even if, malicious code is injected, you can't execute it in the first place. So that is the right idea. But the problem with that is that instead of writing to the stack or heap, an attacker can just write it to somewhere else, or in this case, namely to memory. So we're talking about like RAM or like volatile memory, right? So it doesn't have to live in the stack or the heap. So the problem with this is I, as an attacker, write it to memory, and then I just execute it from there, right? So that's the number one problem, which is, you can just write plus execute code in, and I guess to differentiate it, main memory. Now, one of the defenses, of course, is similar to the NX bit, simply just make the writable parts of memory non-executable. Then this doesn't work, and you'd be correct in making that conclusion. But keep in mind, although this particular exploit, which would be like executing injected code, won't work, that doesn't mean that the vulnerability itself is not exploitable anymore. Buffer overflows can still be leveraged with a different kind of exploit that is called ROP. So hopefully this is familiar, but just as a reminder, this is return-oriented programming. So the idea here is that as opposed to having to inject my own code as an attacker, what I can do is leverage the machine code generated by the program itself, and then through a malicious, well-planned way of executing machine code within the original program itself, and then potentially passing in my own arguments to it, I can still achieve or exploit some malicious behavior by just simply leveraging the machine code already defined within the program itself. So to put that practically, and we'll see this in the short answers later, the idea is kind of like, if you use a conditional, or if you make sort of like a not quite a system call, but maybe sort of if you invoke a method within a method, the problem there is that in machine code, that gets translated to a jump instruction. Hopefully that rings a bell from 61C. So the idea is that the jump instruction takes a memory address and it'll go to that memory address. If I simply locate that machine code and I pass in my own memory address that redirects the program to somewhere that the attacker wants it to be, that would be a very reasonable, very tangible, and very fruitful exploit of the buffer overflow vulnerability. Great. All right, so number 5, if you use a memory safe language, some buffer overflow attacks are still possible. Again, memory safe is our defense, and buffer overflow is the vulnerability, right? So just to make sure we're on the same page, when we refer to memory safe, we are referring to languages like Python from 61A or Java from 61B. And the reason that they do this, and I'll just do a check mark for memory safe, is because they do garbage collection. So the idea here is that memory management as a whole is taken care of and abstracted away and taken care of by sort of the compiler. It's not something that the programmer has to deal with. Now, memory unsafe would be C. So C, being one of the earlier languages, left memory management to be the responsibility of the programmer, which is what leads to functions like free, malloc, calloc, stuff like that, right? So that's not memory safe. Now, the buffer overflow vulnerability spawns from this core idea, or this sort of, it's based on the incorrectly handled memory management, which is usually a product of, wrong development, or maybe not, wrong is not the right word for it, but maybe just like unsafe development or poorly written code, I think is the poorly written code for memory management, right? So in a memory safe language, all of that is abstracted away to the compiler. So all of that behavior of doing frees and callocs and mallocs are hidden under the hood. And as time has shown us, it's been tested and verified to work correctly. So in Python and Java, we can safely code without having to worry about memory management based vulnerabilities, which include buffer overflows. So this is thankfully true. Or sorry, no, it is true that in a memory safe language, you don't have to worry about buffer overflow attacks. So this original claim is false. So some buffer overflow attacks are still possible. That's not the case. Buffer overflow attacks are nothing to be worried about anymore. So the simple answer is that they just, buffer overflow attacks don't work with memory safe languages. Cool. Great. So moving on to the final problem, we have ASLR, stack canaries, and NX together. NX bits all combined, assembled, are insufficient to prevent exploitation of all buffer flow attacks. So we have our defenses in place. And we are saying that buffer overflow is, the vulnerability, and, generally speaking, we have all exploitations based on buffer overflow being considered. So as sort of mentioned before, anytime we make some of these absolute claims, it's likely not true. So even with all four defenses, it is very likely that buffer overflow attacks are still a viable vulnerability exploit combo. So in short, each of these protections can be overcome one way or another. As we mentioned before, with stack canaries, simple information leakage can lead to it being overwritten, or not enough entropy is also an issue. With ASLR, if you might recall, that refers to this technique of doing address, just sort of like randomization. So this is a pretty effective technique, but again, it only makes it harder to do buffer overflow. It doesn't render buffer overflow impossible. So with address space layout randomization, some possible exploits include, using address leaks, like if you've gained access to data relative to a particular address, some implementation weakness, something that is not in scope but is a viable exploit is side channels associated with hardware. That's something you don't really need to worry about. You can Google it if you're interested. But the point is that, even with these defensive measures, they make it more difficult. They make it less likely. The amount of work that goes into writing an exploit is more, but it doesn't prevent all of them. So that's why this statement is true. Great. All right, so moving on to the second phase, now we have the short answer. So these should go by pretty quickly. Great. What vulnerability would arise if the canary was above the return address? So remember, we have, kind of like our local data here. We have, our canary, and then we have sort of a more important set of information down here, including like, the what's it called? Like control data. We have like certain registers that are down here, right? So the problem here is if it's put above the return address, it still doesn't stop an attacker from overwriting the return address. Again, canaries are just for detection, but they by themselves, without any extra software, do not do any form of prevention, right? Now, with that being said, if you use something like ASLR, or if you sort of like translate it into machine code in a way where the attacker could not figure out or had a hard time figuring out the return address, then it's possible that you could use a canary to detect stack smashing. But the idea here is that the vulnerability is, canaries again are for detection, not prevention, which means overwriting the return address is by all means still possible. Great. Number 2, what vulnerability would arise if the stack canary was between the return address and the saved frame pointer? So based on the logic in 1, you can use that again and surmise that an attacker can easily overwrite the saved frame pointer. So what that means is, when the base pointer for a program returns, it goes to the wrong address. It could be an address specified by the attacker. And as we've seen before, when the attacker gets to specify where your program goes, this can easily be turned into an exploit. So I'm just going to say like the saved frame pointer can be overwritten, with with a wrong address. Cool. Number 3, assume ASLR is enabled. What vulnerability would arise if the instruction jump and then pointer to ESP? So you might remember ESP here is a register in memory. So as we kind of alluded to before, by using return-oriented programming, you can exploit instructions already written into the existing program itself, right? So jump ESP is something that would pop up very frequently when a function simply terminates, the return statement is called, and it goes back to the callee, right? So if the attacker can identify this command, it can just overwrite the return instruction pointer with the address of their command. So kind of similar to number 2, right? So instead of jumping to the intended destination, so the function will execute the instruction that's a word or one instruction before the return instruction program, and by putting shellcode after the RIP, the jump command would go there. So I think to keep this simple, with return oriented programming, we can exploit existing machine code, exploits existing machine code. And the idea here is that instead of jumping to the correct address, the attacker can just have it one jump attacker forces jump, I guess, to their own address. Great. All right, we are on the last part of this worksheet where we are going to talk about the trusted computing base. So hopefully this is going to be short and sweet. It's not a terribly complicated concept, but it is an important one to know. Great, so let's start with the first question, which is what is a TCB or trusted computing base? So again, if you haven't done the problem, recommend take a minute to stop and think about it, but I'm just going to dive in. So TCB refers to the set of hardware, software, firmware, anything about your system that you rely upon to make sure that the system is secure. So just to kind of put that into words, and you can find this on the solution sheet too. It's the set of hardware, software, firmware, whatever which is relied on by the system's security, or sort of more technically, for the correct enforcement of system security. So one of the important things to note here is that if anything in your TCB goes wrong, so if any of the hardware or software or firmware, like if any of these components are compromised or discovered to be vulnerable, then the system security is compromised. So a lot of those properties that we guarantee about confidentiality, about integrity, about authenticity, the idea is that these core components, if they go down, then the system is open to attack. Or open to exploit. Now, on the flip side, the idea is if something is not included in the TCP, then if it goes wrong, it shouldn't affect your system security. Maybe some functionality goes a little wonky, but it shouldn't violate any of the security principles that we mentioned from before. Great. So moving on to problem number 2, what can we do to reduce the size of the TCP? So before answering this question, it is noteworthy that we want to keep our TCP as small as possible, primarily for 2 reasons. And for question 2, I'll just put here is like, why do we want to do this in the first place? Well, we do want to keep the cost down as much as possible and also decrease the risk. So the reason the second one is true is because if we have fewer components, if we have fewer things to manage, then in a very general sense, ideally, fewer things can go wrong. If we have 3 things we rely on instead of 4, 3 things going wrong, potentially going wrong, from a very abstract standpoint, has a lower probability than an additional 4th thing also going wrong. Great. So the way we actually reduce the size of the TCP, so the first one, which is relatively straightforward, is simply just like reducing the number of dependencies. So the idea here is, if you build like a web app in JavaScript, which like imports some third-party package on Node, or if you build some, backend server in Python that pip installs some dependency, and then you become aware of the fact that you're not sure if this dependency is reliable from a confidentiality, integrity, or authenticity standpoint, then removing that dependency altogether is a good idea. Now, the second way that you could do this is through 2 techniques. So one is called privilege separation. So what we're saying here is we're sort of breaking up a privilege, and the counter and the sort of thing that follows from it is separation of responsibility. Great. So separation of responsibility and privilege separation. Kind of refers to this idea of like, if I have some very important privilege, what I want to do is break it up. So there's not going to be sort of like a single person or one individual who can sort of do something by oneself. So for example, this goes back to the idea of like if you need two people to fire a rocket or do some really important action, by separating the responsibility into such that there's two keys that are needed as opposed to one key. That's like a good way to ensure that not any one key or not any one access point or something in the TCB, when it fails, takes down the whole system with it. So the idea here is that by separating your responsibility into smaller chunks, you break it up a bit more, and you have more sort of components that in aggregate reflect that original privilege, but not all of them can break your security goals if they break, right? So as opposed to having one person that could compromise the whole situation, if you separate that responsibility among n people, and you say all n people need to come together to make this action happen, then in theory, like if n minus one of them come together to do something malicious, it still won't break your security goal if you just have a smaller chunk of that responsibility part of your TCB. Great. Awesome. So last but not least, we have number 3, which is by no means there aren't any sort of like definitive correct answers, but these are just interesting contexts to get your mind jogging about what a TCB would look like, or how to think about identifying the things that would go into a TCB, right? So usually I guess when approaching these kind of problems, it would be interesting to, going back to security principles, just think about the access points, think about if there are any inadvertent access points that would allow someone to circumvent some desired security principles. So let's just dive in with the practical example. So for part A, we want to prevent a break-in to your apartment, right? So the idea here is if you lock the door, no one else should get in. So right off the bat, your door lock would be something part of your TCB. And then even if you have a really good lock, if you have a really flimsy door that can be kicked down, that's probably not good. So of course the door would also be in your TCB, right? But you can imagine your house has a lot more sort of places of entry than just your door and your lock, right? So whether you have whether it's like a window that's exposed, or like a pipe that's really big that leads to somewhere in your house, if you have walls that aren't too great, if you have a roof, or like a chimney, so I guess like Santa going down the chimney is potentially a security violation, so you want to put the chimney in your TCB to make sure that nobody can come down. And then in addition to the architecture of the house, so if someone finds you, you are part of the TCB because you own the key, and if you somehow give up the key or lose the key, that's sort of like a fault in one of the components in the TCB. So if you lose a key, the whole security guarantee comes apart, so you are part of the TCB. And by that logic, if you give anyone else a key, whether it's your parents, significant other, your friends, or whatever, they are now part of the TCB for the very same reasons. Cool. Locking up your bike, part B. So what are the things that are involved with locking? So hopefully from experiences at Berkeley and with bike theft, you're somewhat familiar with the things that might go into here. So first and foremost, we again have the lock, as mentioned before, but as we've seen, sometimes a flimsy bike frame, or if the bike is sort of poorly made, the wheels and the handlebar and whatever, it can be taken off pretty easily. So just sort of like the bike frame itself, or just sort of like the way the bike is built, that's pretty important too. But even with a very nicely designed bike that doesn't come apart too easily, and even with a great lock, if you don't lock it to something that is secure, then someone could just rip out the post that you've locked it to, and just take the bike and the post away. So the idea is like the post or like thing the bike is locked to is also important. Great. And then by extension, this is in the solution, so I'll just include them here. The ground. If you have a nice cement post that is placed in a very sort of flimsy, very soft like ground, maybe like sand or something like that, then maybe someone's motivated enough to take the lock, the bike, and then the post and the whole thing because it's not attached to the ground. Great. So for part C, preventing people from riding BART for free. So when you walk into the BART, you have the ticket machine that you purchase a ticket from. And when you buy a ticket, the ticket you put into the turnstile, and the turnstile, when it reads the ticket and recognizes that it's a valid one, it opens the entrance, and then you can walk in, right? So everything in that flow of actions that leads to riding the BART in a correct manner, which is not for free by paying for it. So that would include like, the ticket machine working reliably, it doesn't get compromised. You can't just, it doesn't, break and someone can just click a button and get a free ticket. The other thing is like the ticket itself. So, if you can make something counterfeit that's probably not good, then that gets compromised. If your ticket is compromised, and the whole point of having a secure set of gates before riding the BART, that comes down. The turnstiles, maybe you've seen this in practice before, but if they're not working, if they're malfunctioning, if you can just squeeze by, that gets compromised. And by that extension, kind of like, whatever the entrances or, the mechanism for reading the tickets. And then, of course, if you, even with all this, if you have someone that just sort of jumps over the gate, it's kind of up to the employees to enforce the policy. So even if you have something technically very sound, if someone circumvents it, and the person who's there that's supposed to be enforcing the security policy doesn't, then the whole thing crumbles to the ground, right? So by that logic, the employee is part of the TCB. Great. Last but not least, we have part D. So making sure no explosives are present on an airplane. So this is pretty important responsibility. So what happens when you go to the airport? Well, you check into the kiosk, which is for printing a ticket. You go through a TSA, the security gates. If someone leaves the airport, those are designed to be one-way exit gates, so you can't, go back into the airport. If you there are a lot of things to think about, and there's a lot of correct answers that we potentially might not even cover, right? But you can think about this from the perspective of making sure no explosives are present. So you can start from potentially like who can bring explosives, right? So this could potentially be sort of like a passenger. So based on how a passenger ventures through the airport, then you want to make sure, the TSA, security, plus the employees and all the technology associated with like screening and checking your bags, all of that is working properly. Another thing, so the reason that you wouldn't include something like a ticket kiosk, so I'll just put this here and then cross this out, is because if the ticket kiosk malfunctions, that has nothing to do with the efficacy of TSA checking your bags, right? So it's part of the user flow, it's part of the user experience, but it's not part of the system security. And if someone is leaving, one-way exit gates, and whoever is guarding those gates, that's pretty important too. Great. And then something else that could be important is like, if you have sort of like airport employees themselves. And again, this is all based on like what you decide to include in the threat model, right? Like if airport employees are super trustworthy, they've gone through some series of security measures and checks, then maybe they're not part of your threat model. But if they are, then you would include more stuff in your TCB, like for example, around the runway. If you have like fences around the runway, or if you have sort of like the baggage claim and like baggage deploy areas, making sure that nothing is surreptitiously or baggage claim and baggage check-in. Nothing is like surreptitiously checked in. That could be part of your TCB too. Great. So that concludes this discussion. Again, for this last part, this is by no means the completely correct answers, but hopefully that gave you some insight into how to think about the TCB.